All systems go. We are now hopefully live. Hello, everybody, and welcome to another session of the John Chappell Natural Philosophy Society. And yep, it seems to be working. So today's session will be about replacing special relativity with the scalar theory of everything, and that's by John Hodge. And John Hodge has done other talks which have been very interesting. So, first few things. The posting that went out was saying this would be hosted by Ian Karen. He's not doing it. I'm doing the hosting for this session. So let's get into things. First off, it's going to be We Need Your Money. David de Hilster will be asking, please contribute to the Natural Philosophy Society. So I'll post that up now.
Hello, my name is David de Hilster, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Hello, welcome back to me. So John Hodge was with us earlier, and I think we were waiting for him to log back on, but he's presenting us with a video. Oh, he's starting to come back on. Let's see, is he back? Registration. Hello. Hello, John. Can you hear us? Can you hear me, John?
Howdy. The internet crashed.
Did it? Oh, hopefully everything will be all right from now on then.
See your lips moving.
Sorry, your sound's not very good. I think you're frozen now. Oh dear. Oh dear. You might have to try logging off and logging in again.
I'm frozen? I see you as frozen.
You were frozen, yeah. So you right now? Oh, gone again. Okay. So straight on, we'll do the video of his talk, which he's given to us. So we'll go straight to that. And hopefully John Hodge will come back after this talk.
This video is about replacing special relativity in the scalar theory of everything. The Stowe starts from Newtonian optics, interprets experiments since Newton, examines data, not the standard conclusions, and the goal is to explain a wide scope of observations by theory postulates such as galaxy redshift and the Pioneer anomaly, explained by one equation. The Stowe model is causative for forces that cause changes. It is Machian. It is fractal, that is to say all size scales are similar concepts and equations. The physical laws are the same everywhere in the universe. The issue is to discover those laws, making an infinite universe difficult to conceive. A previous episode of the CNPS had the introduction to the scalar theory of everything. And of course, there's a paper on the subject here. This video explores how the Stowe applies to the SR basic observations. Note the data here, not the SR theory. This video suggests measurement should be in relation to a plenum density and the gradient of the plenum density, del rho. This triggers the Machian and causality characteristics of the universe model and the relation of observations of the big, the classical, and the small size scales. And the development of special relativity is based on observations from the 19th century, that is, say, of index of refraction, which is Fitzhugh experiments and the aberration of light, the negative ether drift experiments, that is to say, the Michelson-Morley experiment, and the resulting in the observations, which suggested the Fitzgerald-Lorentz equations. And of course, it also included Maxwell's equations, and in particular, something called the moving magnet and conductor problem, which is a thought experiment. You may remember in the last video, the photon simulation of a single slit diffraction. Here are photon paths. Here are the photon paths through a single slit. And you'll notice, as we noted in the first video, that the photons start to deviate from their path just before or close to reaching the slit, such as you see here. Here we follow the photon's path as it gets close to the atoms, these things, in the slit, and you'll see that they generally change direction, and this should be somewhat similar to the Huygens model. You may remember the explanation of coherence in the photon simulation from the first paragraph. So here we see a couple of photons, here and here, and they're traveling in a row. In the higher row density, the photon speed is faster than in the lower row. Therefore, in time, they tend to line up, which is what you saw in the first video. That lining up is coherence. Another experiment which demonstrates this carry-along effect is the Fitzhugh experiment. C is increased when in the direction of fluid flow, and is decreased when against the fluid flow. That is, the immediate environment of the photon determines the photon's speed and trajectory. Now, you know, this is carry-along, not drag. That is to say, the speed of light is dependent on the rho. The greater rho causes greater tension in the plenum, thus has a higher speed of light. As the Fitzhugh fluid body moves in the direction of the photon spends more time in the relative peak, that is to say, it travels faster. Thus, the photon is carried along at a slightly greater speed dependent on the refractive index. And the Fitzhugh fluid body moves in the direction opposite to that of the photon spends more time in the relative valley of the rho. Thus, the photon is carried along at a slightly lesser speed dependent on the refractive index. Here we see a graph presented in the Michelson-Morley paper. And what you'll notice here is that the big differences appear to be right in here and right in there. Now, you may remember where they are. They're in north latitude, their tabletop where they're doing an experiment is roughly flat to gravity. But if you look at the straight east-west direction is virtually null, which is, okay, it's virtually null. And where the direction is roughly equivalent to where the sun-moon combination is directing opposite. That is to say, this area and this area seems more related to tides than they are to motion of the Earth. So you see, they did detect a difference, but it was a very lower value compared to what they wanted. And it was in a different direction. I say sun or moon direction rather than Earth motion direction. So I tentatively suggest it's the result of a carry-along effect. So experiments rejected the notion of a wind, but not of other ether models. That is, ether is not particles. The world of the sun and moon was at right angle to the effect. Thus, it is a Rho effect. The theory of the luminiferous ether behind the Michelson-Morley experiment is inconsistent with the Fitzhugh experiment. No deviation in the direction of Earth's movement, but the difference was noon and midnight, and so the luminiferous model was rejected. But the STO does have a form of length contraction. And here it is. Here we have a rod and an observer. And we note the center of mass of the rod is right there. We're going to refer to that later. Here the rod has moved in a slightly different position. This is a light ray that was emitted when the rod was in its old position, and the light ray is traveling towards the observer here. Here's another light ray emitted at the current time from the end of the rod, and you'll see that the distance from here and to there to the observer is the same, which means these two rays arrive at the observer at the same time. Thus, the observer believes that the rod is shortened by that amount. So we see here that the measured distance by the observer is dependent on the speed of the communicating thing. If it was other than light, such as sound waves or plenum waves, you would get a different result in terms of its measured length in the observer frame. So here we view where an observer would view the center of mass of the length of the rod to be. If he observes by light, he expects it to be slightly off from the center of mass. If he observes by gravity speed, which is millions of times faster than the speed of light, he would observe it to be very close to the center of mass, which is here. Measuring it by gravity speed is how Laplace and Van Vinderen measured the speed of gravity. Remember all the videos on CNPS that suggested the physical parameter changes caused by velocity, and only velocity, that is to say moving frames alone in the moving frame produces paradoxes. Well, however, a measuring frame may measure changes without such paradoxes, as we're suggesting here. So length contraction caused by velocity is not real. However, we do know that length contraction can be caused by other things such as temperature, etc. The Michelson-Morley experiment was a carry-along effect of near bodies, that is to say the tables, the room, and the sun and the moon. But measurement of shorter lengths in frames moving with respect to systems is real. That is to say, real in that the measuring system measures it to be real, even though the length of the rod is not actually changing. Maxwell's equations suggest fields that transform according to Lorentz invariance. The STO posits Hodge are permanent magnets, that EM radiation signals are Hodge because they travel at the speed of light, And we note that the Coulomb force, which has been measured at many times the speed of light, therefore the Coulomb force is a plenum effect. Here are measurements of the Coulomb force. This is the older paper, but here's a paper where they looked at several different experiments. The moving magnet and conductor problem is a thought experiment, which Einstein considered. And the statement of this thought experiment is that observable phenomena depend only on relative motion, the key here being relative motion. But the customary view of Maxwell's equations draws a distinction between which is moving in a stationary lab frame. Stationary is the special relativity term. Bestow substitutes the word measuring for that word stationary. Bestow rejects thought experiments in general, meaning they should not be used to develop physics models. They may be used to explain physics models, but not to actually develop them. And Bestow rejects Maxwell's equations, and we're going to go into that here in a little bit. There are two types of magnetic field that we explored in the first video. One is where the divergence of that magnetic field is equal to gravity. This is a permanent or Hodge magnets, right? The other type is electromagnetic field, in which case the divergence is zero, as Maxwell suggests. There's an inconsistency between Faraday's law of induction and Ampere's circuit law. We're going to test the Biot-Savart law. In the first video, we had two tests for it. I'm going to repeat one of the tests here with a few extra comments. The Stowe suggests the magnetic effect is ejected from the wire perpendicular to the wire, not in all directions, as the Biot-Savart law assumed with its cross product. This is also experienced in the directionality of radio signals from, say, dipole antennas, which suggests they speed limit on the speed of light. The Stowe suggests the Hodge have a magnetic field and travel at the speed of light. It's the Hodge that are ejected. This is how we're going to test Ampere's law. Here we have a circular current flow in wires and an element of that length of wire right there. And what we're going to concern ourselves with is the difference between the perpendicular, which goes through the radius, which is DC, and not along R. Of course, the Stowe says this current element induces a magnetic effect along its length. And the Biot-Savart law says this R should also be included. You will note in this diagram that if this is the magnet here, that it is not affected by DC, but it is affected by R according to the Biot-Savart law. This is the chronicle delta. So if the magnet here resides in some zone that is perpendicular to the current flow, like in this zone, then it's going to have an effect. If, on the other hand, we're concerned about an element down here, for instance, this will have no effect on the magnet because it'll be directed towards the radius. However, the Biot-Savart law says this element should have some impact on the magnet, even though it's over there. So we're going to do measurements. And here's how we're going to measure it. This is a weight scale. Here we have several disc magnets, ceramic disc magnets. We put them on a wood block so that the magnetic field doesn't impact the scale. And this is our setup. So here we have the circular wire wrapped several times around the center area, power supply putting a current through the wire. This is the vertical of it. That is the magnet with the scale. In the middle of the circle, but at the lower edge of the electromagnet, which we're creating. This is the center position, the zero position. And here we have the magnet near the edge. The Biot-Savart law says that the magnetic field at any point compared to the center, which is what this scale is, should look something like that. The Stowe says no, because remember all that area that didn't have any overlap with the magnet with a larger DM, that should look like that. And you can see that the actual data, these little triangles here, comes pretty close to the Stowe model and rejects the Biot-Savart law. Now we test Faraday's law. Here, what we're going to create changing magnetic field by simply dropping magnets through the coil, as you see here, and we're going to measure the voltage as the magnet drops. It'll be kind of a fast movement. The voltage measured from the dropping in the center and the edge was the same. That's to say, the magnetic field induction is dissimilar to the electric field characteristics. Calculations using the Biot-Savart cross product or the Ampere circuit law are incorrect. There are two different types of magnetic field. One is produced by current, and these are Hodge being emitted from the wire, Hodge being magnets, and the other is the permanent magnets, which is a plenum effect. Free space in the Stowe is the plenum without Hodge. Now, there's an issue here. So a vacuum in a lab is surrounded by walls, which are Hodge. Thus, the plenum density at a point is modified by the Hodge matter around the point. But the plenum is ontologically real, you see, and so it is not a true vacuum, meaning devoid of all real things in our universe. It's a vacuum is where there is no Hodge. In relativity, space-time can be warped and it can direct matter. This is the plenum, or ether in other models. That rose by any name is still a rose, you know. But space-time, that is to say, the left-hand side of the field equation is a result of a math mapping. The S and T are fictitious parameters with no real physical meaning. That is, space-time must be inverse mapped to calculate experimental observations. Therefore, measurement of the speed of light using the left-hand side is invalid. The maximum they can measure on the left-hand side is C. So when you transfer it back to be the real side, meaning the energy, stress energy side, it ends up being something greater than C, which is what is measured. Let us try to conceptually consider the meaning of these two proportionality constants in the Stowe. We consider an analogy with a string, that is to say, the velocity of a wave along the square of the velocity of a wave along the string is proportional to the tension on the string divided by its inertia per unit length. It's the inertia that keeps the string moving in its oscillation. So by analogy, we have the speed of light. Now, we may remember from previous presentation, the Hodge is a magnet which warps the plenum density, which then causes the gravity observations. That is, the Hodge causes a tension field in the plenum density. The plenum has the property of inertia and is the inertial mass of bodies. So the tension is analogous to the inverse of the magnetic constant. That is to say, the speed of light squared is then the inverse of the magnetic permeability divided by the electric constant. The operational meaning then is behind the magnetic tension or pressure and the electric resistance is the perpetual movement of plenum wave triggered by the movement of the Hodge. Perpetual meaning friction is not in the plenum wave, friction is in the loss of Hodge. These waves in the plenum then cause Hodge to move. That is the one and only force in the stove. The Shapiro delay experiment looks at the rate of Hodge movement far from the sun and close to the sun, and so photons travel slower in the lower row around the sun. The speed of gravity, which is the plenum speed of waves, Laplace measured it some time ago by looking at satellites, planets. Lorentz, Poincaré, and Einstein measured it at the beginning of last century or so, and they measured it at sea. But again, what they're doing is they're essentially looking at the left-hand side of what turns out to be the general relativity field equation. Van Flanderen measured it at millions of times the speed of light. He redid Laplace's calculation with modern data and equipment. The Coulomb speed is the plenum speed, and of course we saw this paper before, but it is much greater than c. But in the Shapiro delay, it's so fast that they really can't measure it, how fast it is. It's just very much faster than the speed of light. Another plenum speed application is in quantum entanglement, which is suggested spin. Well, spin is so they can use the angular momentum math. But what the Stowe suggests in these experiments is that what's really going on is the inherent magnetic pole of the particle is actually being reoriented to the magnetic pole in the experiment rather than any kind of angular momentum. Einstein, with the PR experiment suggestion, and Bell in his inequality, attacked the superposition, which is a linear assumption of quantum mechanics. This is Schrodinger's cat thing. That is, say, a state of a system is undetermined until you actually take a measurement. Well, that's a very core idea of QM, but it's not quite right. John Bell looked at this analogy and suggested that we think of socks. So you go to a mall, you ask to see the sock color of someone on the right foot, someone you don't know, it's all, if you want to really do that. Then you suggest that the left foot color sock is the same as that he saw on the right. So if the right foot sock color was red, you say, oh, well, the left foot also has a red color on it. This is a legitimate quantum mechanics experiment. You don't know whether the cat's alive until you open the box. Well, you don't know the left foot sock color until you look. But the hidden variable is that the socks were determined when they were selected. It is not a linear superposition. Bell's inequality that Hodge caused plenum waves that cause direction of the Hodge. In Bell's inequality, the Hodge caused plenum waves that cause the direction of Hodge to change. This is the hidden variable. And of course, the plenum wave travels much faster than the speed of light. See, the Stowe model of photon interference, which explains the transparent mask experiment, which no other model does. The plenum density wave travels at the velocity of gravity, gravity being another effect of this interaction. See how the unity of QM and the big is taking shape. Therefore, all interactions are at plenum speed. They're all non-local in the sense of Bell's inequality. Entanglement, then, in the Stowe model, is wave and particle effect. Plenum wave speed directs the light and has a speed much greater than the Hodge or the photon speed. The photon causes waves in plenum, which is dependent on the number of Hodge energy in the particle. Time dilation, another special relativity thing. In the Stowe, space and time are passive backdrops where the events of the universe play out their trajectories. Space allows movement to and fro, right? You can go to or from some objects. However, time is in only one direction. That is, say, the arrow of time is duration between events. Therefore, processes are not symmetric as current physics of the time parameter suggest. Instead, they talk about entropy, and then the major theories, quantum mechanics and general relativity, really don't think too much about entropy or friction. Science works by using standards which, by assumption, are constant in the experiment. This is usually false, but the uncertainty is within the limits, which makes the resulting model usable. Usable works by allowing uncertainty adjustment, such as done with a GPS system and in the flight of spacecrafts. Measurement standards should be constant for observations for which they are used. Even better, they should be constant throughout the universe, but this has to be assumed. Consider the speed of light as constant results in increased complexity and disagreement with some observations. Space should be measured with rods, but rods may vary with conditions such as temperature, but we know of that variation. Clocks are assumed, they're designed to produce a uniform duration between ticks. Now, a tick of a clock has a physical process that is repeating, and then a counting mechanism, and then you have the assumption that between each tick is the same duration. If either varies, the uniform assumption is violated. Therefore, the use of clock is really just comparing one physical process with another. The time abstract concept is a misinterpretation in physics. The pendulum process has the advantage that we understand the process and its response to various conditions, such as acceleration, or forces, plenum density, and, of course, radiation. The atomic clocks that are frequently used these days has the disadvantage that we do not understand how the decay process works or what triggers the theoretical random process. However, decay processes have been noted to vary annually, and this is not generally known, but here are some papers. This is a guy that has investigated these quite a bit, and you generally don't see this kind of stuff published, but it nonetheless exists and is real. I would speculate that the neutrinos from the sun trigger nuclear decay, but that's just pure speculation on my part. Time dilation in Stowe is due to changing speed of light. That's to say, in the Shapiro delay, what's really happening there is not a time dilation, it is a changing speed of light between the two paths. The atomic clock variation in differing conditions should be considered as data in a model of a future physics decay process theory. The experiments that were used to develop the special theory of relativity were examined in light of the scalar theory of everything. The special theory of relativity should be replaced. The speed of light is the fastest anybody can travel and is dependent on the plenum density. Thirdly, the laws of physics are the same everywhere. You may remember in the STO that all particles are subject to the force of the plenum, that's force, so therefore there is no absolute frame of reference, seeing as all that plenum density is developed by everything in the universe, and there is no Galilean, that is to say, constant velocity reference frame. All particles have a force.
Hello everybody. So Franklin has left us. He's off on some other project. So I'll try adding John Hodge to the screen now. There we go. Oh, what's happening? Hello. Oh, hello. Are you all right? Can you hear me?
Yes.
Great, excellent. I see you've been answering questions in the comments. Is that you finished with that?
Oh yeah, sure.
Okay. So do you want to talk to people?
The online comes first before the questions, I guess.
Yeah. So would you like to talk to people from the green room? Is there a sort of like delay here? Can you hear me? John, can you hear me?
No.
Hello? I think there's a delay on your system. Hello? You might have frozen there.
I'm having difficulty with the internet.
Having difficulty. Oh dear. So the problem seems to be here that is your screen might be freezing and it's
you're frozen.
Yeah, your screen might be freezing and there's a delay. So I don't really know how we're supposed to proceed now. Is there anybody in the green room want to ask some questions? Put your hand up. No. Hello. Yeah, so StreamYard seems to present a lot of problems. People with old computers, they don't seem to be able to get on very easily to it, and I've had to buy a new computer to get onto StreamYard. Going with the old computer, it presented lots of problems. And John's got a new system, but it still seems to be having problems. So, moving on. Can I move on, John? Hi. Hello. Hello. Yep, John's gone now. So, if you're there still, John, try sending me some emails. I'll see let me know what's going on. So, I think John has been answering questions in the comments. If we can go to where he left off. Oh, John's still trying to get back on again. I'll go through the comments after those that John have been dealing with. So from this comment is Question wants to know, would you say time dilation is valid? And I suppose, oh, you there, John? Are you able to deal with it? Hello? Are you able to deal with it? No. No, you're still
Well,
having problems.
Yeah. Time dilation is.
So the answer to that question is yes. There is still a time delay with you.
Not valid, as I said in the video.
Can you send me emails to the answers you want to give to these sort of questions in the comments? Because there's still a time delay with you.
Okay.
Are you able to do that, please?
Put it in chat.
You can put it in the chat. Okay. So that first question, I removed you from the screen. You answer in the chat. Thanks. So Question wants to know, would you say time dilation is valid? And I think John's answer is yes, but I don't know what other things you would add to that. Next. Question goes on to say, would you say atomic clocks in the plane experiment and on Earth were faulty? That's a famous experiment where they set some atomic clocks in aeroplanes and flew around the world. And they decided from that experiment that Einstein's relativity was valid. So I don't know what John's answer to that would be. Next. So this person asked, why does the neutron not decay rapidly in an atom, but very rapidly untethered, according to his solar neutrino comment? Pass. All right, next comment. I think the question's answering to the last person. He's saying, I didn't know that neutrons would decay in an atom. And I suppose that's right. You can't really observe neutrons in the atom. I don't think you got to have the atom emit them so you can observe them, I would think. Cornelius says, in my interpretation, it is because in an atom it is in resonance with the structure of the atom. So it's still carrying on from this original question from inscribed forever. And I still think this is carrying on from this question about neutrino decay. Does that include time delay with velocity as well as gravity? So there is, if you go to relativity, there is time delay in special relativity and in general relativity. So John Walker says, John, what do you mean with speed of gravity? And that's another question. That question is directed at John Hodge. Question says, Cornelius, did you mean that about neutron decay or something else? So in the comments, things are going off in a tangent. They're asking about this neutron decay to be the sort of usual thing with talking about relativity. You can go off in lots of different tangents. And at the moment, they're going on this tangent talking about neutron decay and not really concentrated on the topic of what John Hodge has presented in his video. So question asked, does gravity travel at all? And the problem there is how you particularly defining gravity. Gravity, if you go back to Newton, it's sort of like the apple falls to the ground, and Newton observes that in a kind of like comical representation of that. The apple falls on Newton's head. So gravity is an attraction between the apple and the earth. And you also got the attraction from other things like the moon is attracted to the earth. So that is what gravity is. And then you can start wondering about other things about gravity, such as gravitational waves. And they've done experiments with that, with LIGO and all that. And the mainstream have done experiments with that. And as alternative physics people, we can start to disagree with the interpretation that the mainstream is putting on these things. But it's still going off at another tangent. If you're trying to concentrate on the issue of special relativity, then for the moment you can put aside the issue of gravity and try to think about objects moving at constant velocity without any acceleration and so forth. So this is the problem we're talking about relativity. You can just end up going off in lots of different tangents. Next question. Cornelius, if you tension the phlegm, and this is what John Hodge brought up, the phlegm as the wave carrier, the self-resonant vibrations within it will increase in frequency. This is the time dilation. So I don't know how much that is supposed to be the interpretation of John Hodge. Next. Cornelius, yes, I meant it about the neutron. So you go back to the question about the neutron decay. Unfortunately, John Hodge was supposed to be adding comments in the chat, and so far I haven't seen any from him. Okay, so moving on. So Crest says okay, and I suppose that's still about the neutron decay thing. And moving on to the next one. Question says, does the ether and phlegm differ only with how light propagates, constant or variable? So John Hodge brought up this issue about the phlegm, and I think it's just another version of ether, but really John Hodge would need to answer that. So this sentence from Cornelius, it's broken off as incomplete. Next. So question asks Cornelius, so time dilation does exist, question mark. So it's the private talk between Question and Cornelius, and it's not really addressing the video presented by John Hodge. So what's it? So Cornelius says phlegm, and according to what he said, from what he said earlier, as John says, the ether is the phlegm. So I think that clears up what Cornelius thinks there, and I'm not sure what John Hodge would say, but it's John Hodge has probably got his own version of what he thinks the ether is. Stroke phlegm. So trying to move on. Andrew Castro says, what detector was used to measure the annual change in radioactive decay? And I'm not sure if he's talking about the video now or whether he's talking about this private chat that's going on between these people about neutron decay. So Question now asks about the phlegm, and he says how to tension the phlegm. So I think this is going on to Cornelius's theory, because Cornelius talks about tension a lot when you're dealing with waves. So I think it's still more diversion away from the video that John Hodge presented. And so this is, once again, the problem. We're not concentrating upon the video. We're just going off on a tangent to other issues. So, and I don't know what this question is referring to. It looks like John Hodge is trying to get back on again. And I haven't seen any comments from him in the chat, so he must be having a lot of problems here. So, according to Cornelius, yes, time dilation is real if measured from an alternate frame of reference or gravitational potential. And that's probably in the context of Cornelius's theory. So I can try to call up John Hodge again, see if he's working properly this time with his computer link. Hello, John. I haven't seen any of your comments in the chat. So, no, I think you're frozen. He might be phoning up, trying to get his computer sorted. So I'll remove you again. Let's see what's going on. No. No. So I'm not seeing any comments from John Hodge in the chat. John Hodge is not able to join us. He's having problems with freezing up. And I'm not seeing any emails from him. So communication is sort of broken down from John Hodge. Ideally, I just would like to go off and talk about my things. But actually, I've got a lot of complaints about relativity. The issue I would like to brought up was about Minkowski space-time. Minkowski space-time was not in the original theory of Einstein when he talked about it in 1905 in his paper on the electrodynamics of moving bodies. And it was later on that Minkowski space-time was added to Einstein's relativity. And people like myself, who we are sort of the physics dissidents and not the mainstream, and we start complaining about things like, well, if you added Minkowski space-time to what Einstein was talking about in 1905, it seems to be a different theory. Suddenly, the theory from 1905 is turned into a different theory by adding Minkowski space-time to it. And, well, that doesn't make any sense because that's not being explicitly stated by the mainstream. And so we as the dissidents keep finding fault with what the mainstream is doing. We just don't think they're making a coherent sense of things. And ideally, I would have liked to give them a talk on that. But then John Hodge offered doing this talk on how the experiments could be interpreted a different way for his theory. unfortunately, with that sort of thing, as dissidents, when we decide that Einstein's relativity doesn't make sense, and we go about trying to form a different theory, if we got like sort of 100 people who have reached that conclusion, then those 100 people then go off and form their own particular theory. So 100 people disagree with Einstein's relativity, and they each then form their own theory, 100 different theories. And so we then don't have one theory to present to the mainstream and say, this is the theory you should replace Einstein's relativity by. Instead, we've got hundreds of different theories. 100 people give 100 theories, and if you've got more than 100, well, they give a different theories. Maybe give more theories. So, and that's one of the areas which discourages the mainstream, because when the mainstream say they're prepared to accept that Einstein's relativity is wrong, but they would like to say to us, the dissidents, just present one theory. And we as the dissidents, we can't do that. We just go off in lots of different directions. So we disappoint the mainstream when we come up with hundreds of different theories. But that's the way it is. We're all individual people. We all have our individual perspectives on things. And we can look at Einstein's relativity and see different things wrong with it. And when we see different things wrong with it, we can then come up with a theory based on that. But then that's only particular to our way of looking at it. So I go back to see the comments and see what else we've got coming up on here. If it's still gone off on a diversion about the neutron decay, then that's I don't want to deal with that, because I don't think that was too much of the dealing with by the video by John Hodge. So I'll go through I'll look through the comments in the chat, see what's being said. Publish. So Andrew's talking about decay measurements, and I still think that's a diversion from the video that John presented. So good. I still think that's a diversion. Oh, Franklin's back. Hey, Franklin's not in the green room, but he's managed to give a chat. He tries to get on. So Franklin suggests to John turn off his video if he tries to get him back in. And so like the problem is, I think, with the John system, it is probably an order system. And with this order systems, they don't seem to work very well on StreamYard. And it's probably the issue of the bandwidth. So there's probably not enough bandwidth available on John's system. And so in which case, if he's doing both the video and the speech, then it's using too much up, and then he's freezing. So if he just talked and didn't show his video, then maybe that would be a chance. So I see John's trying to get back in. Let's see if we can get him to do that. Hello, John. If you can, turn off your video and just talk to us. Hello, John. Turn off your video. Can you hear me? Let's call him up.
Yeah, well, I did what
Hello, John.
Franklin suggested.
Yeah. Can you turn off your video and we'll see whether you can just talk?
Howdy.
Hi. If you turn your video off and we can see
I'm
whether...
on the phone now
Yeah.
with
Yeah.
But it's still
So
not working.
StreamYard seems to present to. Yeah. If you turn off your video, please turn your video off, and we'll see whether we can just get you by audio. Because your bandwidth is you're probably not able to cover it.
Meaning what I'm getting, it works.
All right.
Mm.
So my system shows me that you are receiving right now.
I think you might be talking to Franklin. Hello. Right. We had Franklin here. Hello, Franklin.
Yeah, John, you have to turn off your
Kind of
video.
working, meaning it works for a while.
You must turn off your video. Yeah, John, you have to turn off your video.
Meaning it works for a while.
You must turn off your video.
So John has now left the green room. So
Yeah, left the green room again. So
hi, Franklin.
Hello, I'm temporarily back on my high bandwidth connection here.
Yeah, StreamYard presents too many problems.
Yeah, it's kind of difficult with our main guest not being here.
Yeah.
Right, but he did. I would say he mentioned some very controversial things, such as the speed of the Coulomb force is near infinite or greater than the speed of light.
Yeah.
I would have great problems with that. Right, so that's certainly a controversial thing. What did you think of that? I mean, is it is the speed of?
I think it's Van.
Okay, John is back here.
Yeah, here we go.
John,
I'll turn this video off.
Turn off your video. There is going to be something in the bottom that says stop cam. Press stop camera. On the bottom, it says mute, stop cam, settings, present. Please turn off your camera.
No.
The other things that we might be able to help him with is turning off our camera as well. So I can turn off my camera and I can still stop. That also helps reduce bandwidth.
Okay, I'll turn off mine. Bye then.
Yeah, so we can still talk, but
yeah. Hello, John.
John, can you turn off your camera? I'm not sure why he's on the phone.
Don't know. He's probably got a technical advisor. Friend probably knows more about computers, giving him technical advice.
It's a bandwidth problem.
Yeah. But sort of like you're supposed to be giving answers in the comments, but he hasn't been doing that. So people are asking questions and they're going off on a diversion away from his video.
I cannot remotely turn off his camera.
Yeah.
But right now we're not getting anything from him.
I think he'll maybe closing this session down early.
Yeah, it would be kind of difficult.
Yeah, he doesn't seem to be getting the message through about turning his camera off.
And I could answer like some of these other random questions that Andrew was asking about the beta decay having a variable thing, and the way they did that was that they measured the beta decay coming out of, say, nuclear reactors.
Yeah.
And they discovered that the rate does vary seasonally. And it matched the neutrino flux coming from the sun. That's what they matched it up. So that was what that was about, pretty much. Although, once again, there wasn't really anything that John Hodge has to say about that. Although I would say that John should learn how atomic clocks work, because they do not operate off of atomic decay, as his video suggested. No, the atomic clock works off of the radiation which is emitted when the atom is stimulated, much like light is produced when you stimulate, say, hydrogen, it produces certain lines. And then that is how an atomic work. It does not work on like beta decay. So that's why I guess that was kind of related, that there is saying that atomic clock, he said he didn't know how the atomic clock works. But once again, if there's plenty of information on how, say, an atomic clock works, although fundamentally the timekeeping component in an atomic clock is in fact a quartz crystal, which is nothing more than a physical pendulum going back and forth at its resonant frequency. So even an atomic clock fundamentally has at its heart a pendulum, but it does not at all depend upon atomic decay. And and the atomic part is actually just a feedback loop, which is kind of hard to explain. Let's see now. John is trying to come back here. Hopefully we can get him on here.
Oh dear, it's taking too long. Yeah, turn your video off, please. John, turn your video off. Can you turn your video off, please, John? 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 Can you hear me, John? Can you hear me, John? Hello, John? Hello? He might be answering comments now. Hello, John? Hello, John? Hello, John? Hello?
We lost him again.
He's gone again. I see, it's not working. He didn't seem to hear me at all that time.
Yeah, we didn't even hear his audio at all.
No. It's another problem with this StreamYard playing this up.
Yeah, I guess we're probably kind of in a hard place, so maybe we should just go ahead and end the show early if we can't get John on.
I think we should end it. I'm not seeing any emails from him, and he doesn't seem to be giving any comments in the chat, so I can't seem to see anything we can respond to here. So I'm going to end the session. Is that okay, Franklin?
Yep, let's go ahead and do that.
I'll sum it up then. Thank you. All right.
You continue.
Hello. So we just close that comment there. So unfortunately, we're going to have to end this session early. John Hodge has had too many problems connecting into this session. When he's been on, his camera freezes, and we've tried to tell him to turn the camera off, but he doesn't seem to understand, seem to get that message. So he's not able to respond to this video he's presented. So unfortunately, we're going to have to end this session. So thank you, everybody, for your participation. Thank you and goodbye. End session. Thank you. Bye.